Focus area number 2 is artificial intelligence. I actually don't like the word artificial intelligence. I like to call it applied intelligence, because at the root of it, artificial intelligence or applied intelligence requires data. It requires actual data for it to be able to do anything with it. Without data, there is no API. So what we're also focused on, though, with AI is not just AI for the sense of AI. So there are a lot of things that's, especially in this space right now, consumer-grade large language models. You can go as a patient, which I think is somewhat dangerous, go try to self-diagnose yourself by using models which largely hallucinate, largely go off track, and give some advice that I'm sure all of you as providers would cringe at if you saw the results of it. That's not what we want to do. We're talking about applied AI and embedding these solutions right into the challenges, right into the clinical workflows of the Millennium application, right into the Healthy Intent platform, which we'll rename Health Data Intelligence Platform, and I'll cover that in just a second, and making AI a feature in the applications. We'll do the heavy lifting for you, and we'll do it on your data. If you'd like to partner with other systems, if you'd like to join the Health Learning Network, if you'd like to share your data in de-identified form with us or other providers, you're welcome to. If you don't want to do that, you don't have to. And we're still going to give you all the power of large language models, all the power of insights into your data, and allow you to get benefit from this right inside the tool set today. I also think there's tremendous opportunities for embedded AI, for specialty medicine, and for looking at, what's the right size of a data set. If you look at one of the drivers for what's called hallucinations, which means that the computer sort of makes things up, which is why it's actually not artificial, because humans do pretty much the same thing sometimes, right? So if it's a lot actually like we go through a decision process, the difference is the computer can do it far more quickly and far more accurately with large data sets than we can. But think about if you're looking at a specialty data set like pediatric oncology, much better, as an example, much better to train a large language model on only that special data set than pulling a bunch of stuff that doesn't matter. You're going to limit the hallucinations, and it's a misnomer to think that you need incredibly large data sets to actually get intelligence or potential clinical pathways for a particular disease management, as the case may be. We don't need to do that. We can train the models on very small data sets to actually create intelligence, or small relative to the size of the public internet, for example, and we think great things for you in a much more consumable way. So, thinking about AI in general, applied intelligence, artificial intelligence, there are really 3 main pillars to AI. The first is what I call classic AI, which used to be called machine learning. When AI moniker became very popular about 18 months ago, you haven't heard much about the term machine learning. It's still there. It's still the essence. And really what it means is looking for patterns in data, and that allows us to automate tasks, identify disease symptoms earlier, and then move into the generative space. So that's really the essence of it. That's the foundation. Let's look for these data sets, be they big or small, and look for patterns. Even in small data sets, it's easy to miss patterns, particularly when you're looking at spanning disparate providers, as an example. The next piece, which is getting a lot of the buzz today, and a lot of the attention today, is what's called generative AI, or large language models. And what that means is that the computers have become very good at predicting what the next word may be in a narrative. And they do that in rapid succession, and then they put together sentences put together paragraphs, and paragraphs put together narratives. What's shocking is that in the last 18 months, specifically, they've become incredibly accurate. Incredibly accurate. I still think require a little bit of tuning, but pretty good for automating routine tasks like discharge notes, doctor's notes, medication notes, and things like that. And then finally, the other piece of it is high-performance compute, and really running computer simulation, if you will, for things like Seema spoke about, for molecular discovery, and being able to figure out whether or not we can do a lot of the simulation on using computers rather than experimenting on humans very early in the cycle of a new molecule that might be a therapeutic as we go forward. So all 3 of those things are investment areas for us. And all 3 of them require GPUs. And if you're familiar with computer science, you used to see the word CPU, but GPU is not a typo. It's graphics processing unit. And what's happened over time is that it was discovered that GPUs, Graphics processing units are actually far more effective at dealing with very large data sets, and the computational power among GPUs is far more effective than a traditional CPU, a much better fit for AI. So we're investing very heavily in GPUs. It's also no secret that there's a worldwide shortage of GPUs happening right now, and it's not predicted to get any better really anytime soon. So when you want to look at the combination of GPUs and high performance compute for things like molecular discovery, time is money, because you pay by the cycle to consume these GPUs. We can run this, and we can run these GPUs specifically in our partnership with NVIDIA at world-class speeds. In fact, one of the very first things that happened was that an omics company set a world record for a whole genome processing using the NVIDIA GPU chipset on top of the Oracle Cloud. I think you'll continue to see more of these things. I think you'll continue to see whole genome sequencing, let alone and even pathogen sequencing, which is far less compute intensive, to become the norm. And I think you'll see this start to come out as a service that we can offer together with partners like NVIDIA. We're also partnering with Cohere on large language models, particularly trained on medical data sets. Again, the huge difference, unlike some of the other large language models on the market, is that you control the data. If you want to keep your data in your cloud instance and you don't want to share it with anybody else, you don't have to. You'll still get all the benefit of large language models and not having to join forces. If you like to join forces in your data with other providers in a de-identified model, I think that's going to have great utility as well. So really, by doing all that, we're activating systems of intelligence, and we're creating systems of record into systems of intelligence. And I think if we look at, particularly if we go back to the EHR for a second and the genesis of EHRs, which were constructed by billers and are largely transactional systems, there's been a lot of trying to morph and merge these things into better systems of intelligence. AI can really take these traditionally transactional systems and we think completely turn them into systems of intelligence, meaning that at the point of care, they can make better decisions and help you make better decisions for your patients rather than having to punch out the different systems or go run models or go have somebody in your informatics department go try to look at some patterns for you. We need to be able to do that right at the point of care. That's true for care pathways, that's true for reimbursements, that's true for adjudications, that's true for approvals. All of those things with embedded AI are happening, and we're incorporating those into our systems today, along with digital assistants and voice recognition as well.